Richard Socher is currently chief scientist at Salesforce. He got there through actually starting a company, MetaMind, one of the first deep learning companies. This is before every company was an AI company. Was acquired by Salesforce as chief scientist there. Before that, Richard did his PhD at Stanford, establishing many of the first results on deep learning for natural language processing. And it's something that might be hard to kind of realize now, but back then there was a lot of skepticism actually that deep learning could work for NLP. A lot of people said, yeah, I get it, deep learning for vision. It's a pattern recognition problem and it's continuous. I can see how that might work, but language is all discrete. It doesn't seem the right fit. Richard and some other people elsewhere on the process also proved those non-believers wrong and has pioneered a lot of the NLP progress, also has been originating and often teaching the deep learning NLP class at Stanford, from which many people learn their deep learning NLP skills, and we're very happy to have Richard here today. Please join me in welcoming him.
Thank you. All right, we'll try to make this exciting. We've had a lot of talks in the last couple of days, so if you have any questions in the middle of the talk, I think that can make it more interesting for all of us. So just raise your hand if anything's unclear. So I'm very excited to talk to you today about what we in short call the NLP decathlon or decaNLP. It's basically a multitask learning framework for most, if not all, of natural language processing. And I want to give a big shout out to Brian McCann, who is the first author of this paper. I pitched this idea for over 2 years, including why don't we do everything as language modeling and question answering ideas to various people. And they just said, no, this is too complicated. It's too much pre-processing. All these different data sets have a different notion of what a word is. Is wasn't, like was, space, N apostrophe T, or is it just one word? And lots of intricacies. And when you actually pre-process it, it took several months to just get all these different data sets into the right format, so that now we can unify a lot inside the field of NLP. And then Nitish Kaskar helped us a lot on the optimization side, and you'll know what I mean about that in a second. And Saming Xiong is our director of research, and he's helpful in pretty much all our research projects. So there are a couple of questions that I had when I've sort of started looking a little bit higher level of what happened in the field. In the sort of pre-2010 past, machine learning was mostly successful when there's a lot of manual feature engineering, where experts in NLP would look at like, oh, these are positive words and these are negative words, and then just kind of assigned a weight to each of these words, and then they look at features, look at errors, and they're like, oh, negation is a thing. And so you're like, not one of those words is another feature that we can weight. And then people kept engineering these features in pretty much all the different aspects of NLP. And then in 2010, we started with some pushback from the community in the beginning to push deep learning for feature learning. And now I think we're currently in the state where we do a lot of deep architecture engineering for single tasks. And in some ways that's exciting, and I'll talk a little bit about it in the next slide, but I sort of asked myself the question, okay, what's next? What will be a major fundamental change again that might come up in the field, and how can we actually make that happen more quickly? And so when looking at the limits of single task learning, I kind of felt like as a community we're kind of like this dog, where it's clear that basically we can get great performance improvements when we take a specific data set, a specific task, a specific model, and then try to just hill climb on a particular metric, right? And as long as we have, and this is a rough estimation, but as long as the data set has at least 1,000 examples per class, we can probably get now into a range where this could be put into a production system. So ImageNet, 1,000 classes, each class has 1,000 images, so roughly 1 million images, and you do pretty well in ImageNet. Language translation, well, there are a lot of different words, so you want to ideally have many millions of words to starting to do well enough in machine translation, and so on. But it's also clear to me that if we keep doing that, we're not really going to end up with some general AI system, that we instead actually should be trying to continuously learn and have a single model that gets better and better over time. Just like our brain isn't swapped in every time we try to solve a different task. And so in most cases, models are starting most of their weights from random. And of course, that's not quite true because we also have pre-training. So let's look at pre-training for a second. You've all learned about ImageNet and convolutional neural networks already here and elsewhere, I'm sure. And so in computer vision, there was sort of this single blocking task. Like if you can't even tell a cat versus a dog versus a car, it doesn't really make sense to do anything else in vision. And so everybody agreed on that and saw that as a major milestone when deep neural networks were able to significantly improve accuracy on ImageNet. And what's interesting is then people took these ImageNet pre-trained convolutional neural nets and basically assumed some of those weights were already pre-trained through ImageNet training, and then they just kind of changed the last layers or changed some parts of the architecture, and that was a big performance improvement. Now in NLP, the story is a little more complex. We basically have mostly been able to only pre-train the word vectors. And who here is familiar with word vectors? Can you raise your hand? Awesome, great. Basically, we've had word2vec, and then global vectors, and then we have contextual vectors that kind of trained words, not just for single vectors, but sort of in their context of a sentence, and then try to predict the translation. And then Elmo kind of replaced the translation bit with language modeling instead of translation, which is nicer because you have even more training data, but had similar architectures. And then BERT's kind of another step towards that with yet another architecture and some slight modifications, not quite language modeling, but sort of predicting words in their context, not just the next word, and some other tricks. And so basically, in some ways, we're still kind of stuck at the first couple of layers. For the majority of time until last year, it was just the word vectors. Now it's like 1 or 2 layers above the word vectors, but most people still see that as kind of we take this as a pre-trained resource, and then we're going to still do a lot of other things with the model that wasn't pre-trained. And you might ask, okay, why has there not been more weight sharing and model sharing in NLP? Why aren't we just like in CNNs kind of sharing all the layers almost all the way to the end? And I think part of it is that NLP requires many different types of reasoning, logical reasoning, linguistic, emotional reasoning, right? You can, in a sentence, describe, well, 50 people in the room, 29 left, are there still people in the room? And it's a very logical kind of thing. And that's one part of NLP. Another part of NLP is you say, this is a typical Nicolas Cage movie, and you need to know if that's positive or negative. And if you have reasonably good taste, it's probably a negative review. No judgment, just a joke. And then you have visual reasoning, so there's all kinds of different things going on. And I think because of that, it was a little too daunting of a task for the community. So the community in the last couple of decades kind of split up all of natural language processing into a lot of very small, discrete tasks. And I'd argue that in some cases we actually had somewhat of an artificial splitting of these tasks, and looked at very low-level tasks like just extracting named entities, like is this an organization or a location name and things like that. And then we've seen a lot of what I would call benchmark chasing in each of these sub-communities. And so to make more progress, some people argue it has to be kind of all unsupervised. And I would argue that that isn't going to be enough for natural language. If you put like a child into the jungle, they'll probably learn a reasonably good visual cortex, but they're not going to learn language just by themselves, right? You have to have some kind of communication, some kind of supervision in both nature and I think for computer systems too, and when it comes to language. And so now you might ask, okay, why does all of this, these reasons lead to trying to work on a unified multitask model for most of NLP? And I actually think that multitask learning in particular is a major blocker for general NLP systems. And that if we can have a unified model to decide how to transfer knowledge between these different NLP tasks, and I'll give you a bunch of examples very soon, then a lot of things could naturally fall out of this. Domain adaptation, being able to train on one type of domain like movie reviews, and then being able to do sentiment reviews for restaurants or products very quickly. We can have more weight sharing. In fact, when I say weight sharing, I want to share all the weights, including the output layer, including your softmax classifier at the end. Basically, the entire system should be pre-trained. And then that will hopefully lead to a lot of transfer learning and eventually zero-shot learning. And so also, I think once we can get a unified framework, just a little bit similar to computer vision, where basically you'd be crazy to not try a CNN for any vision problem that you'd have. If we have something similar for NLP, where we have different formats and so on, we can adapt it more easily to new tasks. We can, and this is kind of a more production level type thing, less a research thing, but I think making deployments more straightforward and faster. Right now, you have like a translation team, and you have a chatbot team in your company, and so on, and they're usually different teams. They use different models, and they're not sharing as much. And then I think just like with CNNs, where now you can train like a squirrel detector and connect it to your sprinkler or something as like a kind of amateur programmer without knowing all the depths of CNNs. I think if we had similar frameworks for NLP, it would also lower the bar to do very interesting and unique things in the field. And then my dream would be eventually to have a single NLP model that as we learn new things, as we want this to learn new things, we just keep making the system smarter over time. It'll just learn more stuff, and we'll get, in the end, a very general NLP system. And I think that is kind of an obvious blocker towards even AGI. There are lots of other blockers, but to me this is an obvious one. So how can we then express all these different NLP tasks in the same framework? Well, at first, I think you can kind of group most of NLP tasks into these three categories, namely sequence tagging, text classification, and sequence-to-sequence problems. So in tagging, we kind of want to give a single label for each word. Named entity recognition is a good example. You talk about a bunch of products and customers. You want to extract like who are the customer names, what are the product names, what are the dates, what are the locations of headquarters or whatnot, and analyze email or news text corpora and so on. Text classification, fairly straightforward. Just give a single label for an entire document or tweet or whatever it is. And then a lot of tasks are in the sequence-to-sequence framework, which is basically machine translation. German sentence comes in, English sentence comes out. Summarization, long document comes in, shorter version of that document comes out, and question answering. And I actually like those three tasks the most because in some ways they're the most immediately useful tasks in NLP. Like you might say, okay, named entity recognition, I take that system, I put it in some other system, and then maybe that will be something useful. But these last three tasks here are just like immediately somebody will get it. Like why is that useful? An end user really benefits from improvements on them. And so all of that thinking led me to kind of think about what I ended up calling the three equivalent supertasks of NLP. Namely, every NLP problem can be cast into one of those three frameworks, and they all can be mapped to one another too. And they're basically language modeling, question answering, and dialogue systems. And so language modeling, for a long time my group had like the state of the art, and I pitched this to several people, and I wish they had taken me up on it, because now obviously language modeling is really, really useful for a lot of things. But basically, if you can predict the next word accurately, then I can just ask you any kind of question, and then the next couple of words that you predict would be the answer. So what's the translation to German of the sentence, I like this class? Well, it's just like the next couple of words should just be that translation. And you can also ask a question, like what are the named entities, what is the translation, what is the summary, and so on. And you can also cast all of that into a dialogue. But then in the case of dialogue, right now, unfortunately, there aren't really good dialogue systems out there. And we don't really, in most cases, would have a very long dialogue. It's just like, what are the named entities? You give it, and that's like a one-step dialogue. So basically, due to all of these considerations, we chose the middle one here. And this is how we now look at pretty much every NLP problem out there. We think of it as having a context document about which we ask a question, and we generate an answer. So in the first example here, and these are the actual texts for the data set. In the first example here, we have like a Wikipedia paragraph, and this is the Stanford question answering data set. You ask a pretty factual question, and the answer here is an extracted phrase from that context. But you can also have a context of just a single sentence, and you ask what is the translation from English to German, and the answer is, der Großteil der Erde ist Meerwasser. And then you can also have context of a longer document asking what is the summary, and you get a shorter version of that. Well, here the summary often includes some words from the context, but also created some new words. You can do so-called entailment or natural language inference, where you try to understand whether a sentence logically entails or is contradictory with another sentence. And this is another very popular one, sentiment analysis. And this one here is has an interesting detail, namely, we don't just ask what is the sentiment, but we actually include the potential labels that we want the system to predict in the question itself. So is the sentence positive or negative? And this will actually be part of the reason why we'll be able to do zero-shot learning in the end, where we can ask new kinds of questions about new labels, like is Richard happy or sad when nobody clapped? And then the system will actually be able to answer questions it's never seen before, which I'm pretty excited about in some cases. It doesn't always work, of course. And so on. So there are a bunch of others: zero-shot relation extraction, semantic role labeling. We can also translate natural language English questions into SQL queries. Very useful task. Also kind of like translation, but not quite human machine translation, but more into SQL. And then these are sort of Winograd schemas where you try to find out, based on small changes here, try to reason over basically anaphoras or co-reference. So these are basically the 10 tasks. And so now that we think of the question as part of the inputs, what that means is actually we're kind of doing meta-supervised learning, where usually the task definition is kind of outside of the machine learning model. It's just something you know in your head, and then you give an X input and a Y output. Here we are adding the task to the inputs of the model, and so that way the model can learn itself how to adapt to different task inputs. And in our case, we phrase the task as a question. You don't always need to have a proper question. So in the case of summary, it's always the same question: what is the summary, what is the summary? So you could just say summary token for this task. But then in several, over half of the data sets, the question is actually different for every single training example, what's the major importance of Southern California or something like that, and different SQL translations, or who had given help, or in classification cases you have the labels in here, and so on. So it depends on what you're looking at. And so it makes sense, since we're doing NLP, to keep the format of the task as a natural language question. All right, any questions so far? Now that everything is a question. Yes?
In semantic entailment, how do you decide the context is not the two sentences, like question answering, like sentiment analysis, but instead the question can be just, is this an entailment into the contradiction?
Great question. So you could not include the hypothesis here. You can put hypothesis and premise in here and then just ask, is this entailment, neutral, or contradiction, right? In some ways, it's an arbitrary choice, and you could just try both. And we did try both, and I think this worked a teeny bit better. Yeah, and in some ways, some of these are, you can ask a similar question about what should you sometimes include in a context versus the question, and it's actually in several of them, you could argue to put them into different things. Yeah.
I had a similar question. I didn't quite understand how you could map question answering to language modeling, for example. I kind of understand it in a fuzzy way, but not quite clearly how it is.
So question answering to language modeling. So in some ways, in language modeling, what you're trying to do is, given a context, you try to predict the next word. This is the context, and then you add the question to the end of that context, and you try to predict the next word, and that would be your answer. Awesome. All right. So basically, we have a couple of design considerations. We don't want this final model to just be like a classifier. If summarization, then run this model. If translation, run this other model, because that would obviously not give us all the transfer learning and general AI systems capabilities that we want. So we want the model sort of internally adjust to these. And so this is basically the final summary of the model. We will start with a context, ask a question, and then we'll generate the answer words one word at a time. And there are three ways we can generate a word. One, we can point to a context word. based on the hidden states that we'll go through in the next slide. 2, we can point to a question word, or 3, we can run our standard softmax classifier and predict a word from some external vocabulary. And we'll have a very simple pointer switch mechanism that can choose between these 3 options. So you can actually check out all of the code and leaderboard and everything on this website, decaNLP.com. And just to give you a brief hands-on thing to show what that looks like, maybe. Oh. This is the GitHub repository. Actually kind of excited that it has a lot of stars and forks. But you can basically run everything, all these experiments, with a single sort of command. And it will download all the data sets, do all the pre-processing, and train all the models, and you can test it. And it's all kind of simplified. So any NLP task where you can pre-process your task into, here's a context, here's a question, here's an answer, which I think is pretty much every NLP task. You can just use this off the shelf, and it'll do something. And in many cases, it'll do pretty well. All right, so we're going to go over this model in a little bit. Can't go into too many details. Fortunately, hopefully, most of you already know a lot of these standard components. In some ways, it's kind of like the first CNN that did really well in that there's not that many novelties in this model. It's just like how you put it all together and carefully tune the whole thing. So we have glove or eventually cove word vectors. We also have character n-grams in case you don't have a word in your vocabulary. They are mapped in a linear layer, and then we'll have a shared bidirectional LSTM that is shared between the question encoder and the context encoder. Then we have this co-attention mechanism, which is essentially just an outer product between all the hidden states of both of those sequences. So you basically get an interdependent representation of both of these sequences. Then we have a couple of transformer layers, which are essentially self-attention. A lot of outer products also. Will take a little too long to explain the details if you're not familiar with transformer layers, but I encourage you to read it. It's really the baseline or the base model for BERT and a lot of other interesting things. The nice thing about transformer layers is they're fully parallelizable on GPUs. Unfortunately, they're still very brittle to tune. Maybe we need more experts to really dig into all the details on how to tune them well and make them a little more robust. We tried to only have transformer layers too, but it really didn't perform well. We needed these LSTMs in a couple of different places. And then we basically generate, in this sort of standard autoregressive decoder, one word at a time, where in each case you can basically compute the distribution for these hidden states of potential words in the question and the context and the vocabulary, and you kind of just sum up those 3 distributions in a weighted way. Again, code is all online, relatively standard components of LSTMs, transformer layers, and pointer mechanisms, and this co-attention that we and others have invented a couple years ago. So now, what are the data sets that we evaluated on? We want to make sure that they're all publicly available, so there isn't any reason you have to like sign up and pay some big membership fee or something. And so that's one of the reasons. You can basically wget and run all the experiments yourself on your own machines. And then there's a lot of different evaluation conventions inside each of these subcommunities. We're thinking if we could unify it all into some normalized F1 score, but then in the end, all of these metrics are actually between 0 and 100. And so we kind of decided we stick to the standard metrics of each field. Blue and rouge scores, for instance, for translation summarization are sort of differently weighted n-gram overlapping scores because you might have different but also reasonable translations or summaries of a document. And we basically define, after a lot of contemplation of whether we should weight the scores based on the data set size and so on, we decided we'll just sum up all these 10 different scores. And you'll actually notice that if you look into this, it's kind of tricky because translation, for instance, that data set and SQuAD, the Stanford question answering data set, are much, much larger than pronoun resolution Winograd schemas. But you might also argue that Winograd schemas are a lot harder, it's less statistical, needs more reasoning and so on. So we basically decided on that. And now this is the summary of the results. And There are a lot of numbers here, but I'll walk through some of the highlights and the most interesting bits with you. So first, on the left side here, these four, each number that you see is a different model. I mean, it's all the same architecture, but it's trained separately on its own task. And we start with a sequence-to-sequence baseline. We have 10 different models trained on each of these tasks to get each of these numbers. Then we looked at self-attention, then the co-attention layer, and the question pointer mechanism. So a couple of ablations of this model. And then here, these four columns are basically four different models. So this is one single sequence-to-sequence model trained on all 10 tasks combined. And so are these other three. And so a couple of observations. One, the transformer layers really helped in a couple of data sets quite significantly. Number two, question answering and semantic role labeling have a strong connection. So semantic role labeling is things like, is this a teacher-student relationship, or a product-consumer relationship, or things like that, or an agent that is doing something with an object. So a lot of different kinds of semantic relationships that you might have. The pointer mechanism to the question is very important for a couple of examples. Really changes quite significantly, almost doubles for some of the scores. And then multitasking helps in the case of zero-shot relation extraction. And this is pretty exciting, because in some ways I'm more excited these days about some of these zero-shot results than I am about another 1 or 2% improvements on some benchmark that people will kind of tune regardless of whether we work on it or not. But one sad observation here is also that after quite some time, there's still a gap that if we had an oracle that could perfectly separate the 10 tasks and then trigger 10 separate models, it would actually do better than if we had a single model that does all of that. And in some ways, this is a particular choice that we made, and that is, in transfer learning, most of the results, almost all of the results you will read about, are positive results, because people selected data sets that are known to transfer well and help each other. So part of speech tagging, with knowing whether something is a noun or not, turns out that helps if you try to find named entities, because they're all nouns. And it turns out if you do question answering and you train on another question answering data set that's kind of similar, kind of different, then they also help each other. But if you're trying to answer a bunch of things in English, and then you try to translate into German, and then also into SQL, it turns out those have nothing to do with each other, these kinds of tasks. And so in most cases, what we observe here is, in sort of a third of the cases, what is called catastrophic interference or catastrophic forgetting, where these sort of dark truth of or unspoken kind of knowledge in the community is that when tasks help each other, you get transfer learning. When tasks aren't really similar, you get catastrophic interference. They actually hurt each other. And it's really hard to publish that, because nobody wants to hear that stuff doesn't work. But it's actually, I think, really important for us to focus on these kinds of issues also in the community. Now, so far, the training was kind of a standard fully joined training, where we basically took each of the tasks, we'd sample a mini batch, and then we take that mini batch for that task, and we update the model, and we just kind of go through all the tasks. Now, it turns out that you can read papers on so-called curriculum learning, where the idea is you start with simple tasks or simple problems of your domain, and you successively go to harder and harder problems. It turns out in really hard, large multitask learning, it's actually the opposite of what you need to do. What you should be doing is what we call anti-curriculum learning, where you start with really hard tasks like translation, question answering over all different kinds of Wikipedia paragraphs, and then you do the easier things like sentiment analysis that just kind of classifies things into two different categories, positive, negative. And so this is kind of the anti-curriculum pre-training, where you iterate first over a couple of the harder tasks, and then you add the simpler tasks later. If you do that, we already get a huge jump here, over 9% or so, and are getting closer to this gap. And now, after that, we spent a couple more weeks/months on tuning this even more. In the interest of time, I won't go through all the details, but basically, we can use better word vectors. We have even better sort of pre-training strategies. And then we can basically include more tasks in this anti-curriculum strategy that we go through 4 or so. And in the end, we basically tune everything a little bit more, and now we're less than 2% in the gap between a single model that is all 10 tasks versus 10 separate models that do it all. Yep.
When you were saying you have to train with more complex tasks first, is there a reason why, or?
I mean, there are. The main idea, I think, is that if you train this whole model to
Just adjust your model because you're getting a lot of noise from the code. Let me take that off.
Okay, just take it off. All right, let's party now. All right, so the main idea of why that happens, I think, is that when you train the whole model and everything is shared, right, all the weights are shared, on just sentiment, all the model weights will start focusing on just the outputs are positive, negative. And so all the weights start all the underlying layers and everything are very focused on a very simple problem. And if you then want to take all those weights and now push all the weights to do something much more complex that deals with a much larger vocabulary and different output spaces and so on, like all of German words and all of that, then it's just very hard to pull them out of these local optima that you're stuck in for a simpler task. That's kind of our interpretation. All right, little bit of analysis. The model turns out to be very good at knowing how and where to point to answer different kinds of questions. And now sort of on the positive side, why we're doing all this trouble? Well, one is I mentioned this pre-training thing. I want to pre-train not just the word vectors or the first 2 layers, but I want to pre-train the entirety of the model. And if you do that, and then you take that pre-trained model and you just run it and train it on something else that it's never seen before, and yet another task, like another translation pair, like English to Czech, or another task like named entity recognition, which wasn't one of our 10 original ones, then it turns out this pre-trained model, just like ImageNet pre-trained CNNs, will converge faster and work also slightly better than a randomly initialized model. And what I'm even more excited about than that, where you kind of still train, are zero-shot domain adaptation and general zero-shot kinds of problems. Whereas we trained this on movie reviews, the Stanford Sentiment Tree Bank for sentiment, and then we just ran the existing model that was trained on all these 10 different tasks, just the general NLP model, and immediately it got over 80% accuracy on Amazon product reviews and Yelp restaurant reviews. So if you're a practitioner and you just want a model that is reasonably well on sentiment, you can just use this off the shelf. You don't need to retrain anything. There's another natural language inference data set, similar sort of about entailment and so on, but over a very different kind of domain. And it immediately also got to a reasonable accuracy. And then when you fine tune it, it gets even better, and again, is better than a randomly initialized one. And the last result is kind of the most interesting one. I mentioned this pointer mechanism and including the label of the task in the question. And so then I said, well, could we just ask questions we've never asked before? Like John had a party, but no one came, and he was all alone. And now I ask, is the story sad or happy? And it turns out that the model could do a lot of things, right? It could generate random German words, SQL word, based on this never before seen question, it learns to point to this particular adjective. Even though it's never seen, here's a training corpus of 1,000 sad stories, 1,000 happy stories. Now, you do this classification problem with this new softmax classifier at the top. And that's kind of amazing. I mean, it doesn't always work, right? You can fool it. You can start to rephrase the question and kind of be a little adversarial about it. And it's not super robust. But the fact that it ever works, given all the things it could be doing, is kind of incredible to me and very exciting. But it's also clear we should probably create more of these zero-shot examples. So we have a complete zero-shot test set. All right. So kind of went through all of this quickly. I hope not too quickly. But basically, I hope I could convince you to check this out, decaNLP.com. It's basically a benchmark set, but with the MQAN model, the multitask question answering model, kind of comes also with a first model to tackle this benchmark. And I think it'll be a great framework for us to really understand and improve more general language understanding, multitask learning, domain adaptation, transfer learning, weight sharing, similar to sort of pre-trained ImageNet CNNs, and eventually, I think sort of the holy grail of natural language processing, which is zero-shot learning. Now, there's a ton of work and a ton of papers I would encourage you all to read. Our original conference paper submission had over 100 citations that it had, but these are sort of some of the papers that sort of modified our thinking the most. And I do think sort of one potential answer for what's next in NLP after sort of we've all done a lot of architecture engineering is to try to develop sort of more general architectures and make, just like we made feature engineering obsolete with deep learning, we can try to make architecture engineering obsolete and try to gain, like, in the end, a single great generalized NLP model. All right, thank you. Do we still have question time? A little bit? All right. Yeah?
Hi. The architecture in your decaNLP, so is that your preferred architecture now over like your previous stuff like dynamic memory network?
Yes.
That's my first question, sorry. So my second question is, are you going to go towards visual VQA?
Great question. So the question is this our default best architecture? Yes. Like most things, when you look into the results, you actually realize that we have a couple of state-of-the-art results with this architecture. So this SQL generation, for instance, this is kind of just the 9th task. We're thinking, oh, what other tasks should we throw in there? And it turns out that we got state-of-the-art on SQL generation. And so a bunch of people in that space have then started looking at the model. It really, you have to have the soda label to get people excited. But I think in general, it's a good starting point for pretty much every NLP problem out there. And then, what was your second question? Oh, VQA. So visual question answering is super cool too, but in some ways, I have two problems with it. One, it's kind of hard to find really useful applications for it, like in production ever, like even in like 5-10 years, like even if you could do perfect visual question answering, I can't quite see like good products for it. And then the other thing is we can't even do like textual question answering in all of its glory properly. So until we can do that, we work on VQA, but it's kind of not part of this project. I think eventually, once we've done better on this, it'd be great to have different modules of stimuli that come in and then try to train an even more general model on all the things. Yeah.
So I also have two questions. The first question is how is it possible to create knowledge base? Like many people talk about knowledge base. And we see that domain-specific knowledge base was scientific work. But I don't see any work that connects the knowledge base to the actual like NLP engine or something like that. And how is it possible to use the knowledge graph that is created in the conversational AI? The second question that I have is...
Let's do the first question and we'll do the second question. So this is it's a great question. And my hunch is that you can have different kinds of context, right? You have the question, and then you have the sort of standard document context. But it actually, I think, would make sense to have potentially, it would be nicer if it was all end-to-end trainable, but you could have another module here that basically is a fact retrieval engine, and that just does some really fast IR. And then basically, given these two kinds of queries, kind of throws in a couple of additional facts from a knowledge base, and then also allows you to pay attention over these triplets of a knowledge base. And then I think you could incorporate it into that, which would be pretty cool. All right, what's your second question?
So in many industrial fields, for example, space, we have lots of acronyms, which are the same as acronyms, like the form is the same as acronyms that we see in the everyday work, but the number of acronyms that is repeated in the scientific or a domain-specific literature is limited. How is it possible to take over that with zero-shot learning or a few-shot learning?
So how would you deal with acronyms in these settings? In some ways, acronyms are tricky, but not that hard. So I think n-gram embeddings will basically have to do, especially for new acronyms you've never seen before, we'll have to do it. And then there are actually some papers on learning word and n-gram embeddings from like 1 or 2 examples based on that context, and that's the best you can do at that point. Yeah. Yeah.
So we usually do learning. So I'm wondering, to give an example of a new task and an old task.
Yeah, that was the IWCLT, English to check, and then named entity recognition. Those were unseen tasks, and then we basically looked at those. We had these two experiments here that were unseen tasks that weren't part of the original ones. These two right here. And then these were all also unseen data sets. Yeah.
So following up on what you were asking about, so these unseen tasks, like the SNLI, I'm assuming these are the relatively larger data sets, not small data sets with 2,000.
Yeah, these are all reasonably sized data sets, and these two are also here. It's not complete zero shot. It starts higher and much better than random, but obviously if you want to generate check words and you've never seen anything in check, then it's hard to generate them completely zero shot. Yeah.
So in this, have you also tried this on these data sets, fine-tuning on data sets that are relatively quite small? Like a big problem for practitioners would be, I have a lot of unsupervised data,
Right.
very small data set of which is actually data.
So I don't have results here, but I can tell you that Winograd schemas only has a few hundred examples. It's a really tiny data set, and we did observe a lot of high variance when you train it, and we have to kind of take it almost at the very end. It's very simple. Just learn to point to nouns and personal pronouns and things like that. And so this is kind of the smaller the data set is, the further at the end of the training do you want to do it, and it's going to be still high variance. You need to kind of really check on your small def set when the peak, when the data set performance peaks.
We're looking at NLP transfer learning for NLP, and we're currently looking at some other techniques like BERT and ULM. Would you suggest we go home and look at this?
Yes, I do. All right, last question. That was an easy one. All right.
Quick one. Why didn't we use Elmo or like something like co-vector?
So one of the big improvements was actually using co-vectors that gave us a big boost across a bunch of things. And then Elmo is kind of like another 2% improvement on some other data sets. But we actually did this before Elmo came out. So it's hard, like, you don't want to like have a paper and then every time somebody gets a new word vector, you just like have to rerun all your experiments. So that's the main reason. Awesome. All right. Thanks a bunch. Have a great Sunday evening.